Hello everyone and welcome to Calc Lesson number 24. Today we are going to be doing the second day of section 2.6 related rates, and today we are going to be focusing on problems involving triangles. Okay, so let's jump right in. This says a ladder 25 feet long is leaning against the wall of a house. The base of the ladder is pulled away from the wall at a rate of 2 feet per second. So you have these boxes. They're similar to what you saw yesterday on your packet. I just added this box in the top right corner here so that I could draw a picture to help us visualize what's going on. So we have a 25-foot long ladder leaning against a house. So here is my ladder leaning against a house. And I can see that what I've created here is actually a right triangle. So when I go to determine my relevant formula, I want a formula that's going to relate the sides of my triangle, my horizontal, which I'm going to label as X, my vertical, which I'll label as Y, and then my diagonal, which I will label as Z. And we know to relate the three sides of a right triangle, we can use the Pythagorean theorem, which says x squared plus y squared equals z squared, where z is our hypotenuse. From here, we want to fill in everything that we know. So we were told that the ladder is 25 feet long. So I'm going to fill in my first known quantity as z equals 25. Leaning against the wall of the house, the base of the ladder is being pulled away, so the base is my x value here is being pulled away at a rate of 2 feet per second. So the rate of change of that x, or dx dt, equals 2 feet per second. And then for part A, we want to determine how fast is the top of the ladder moving down. So we want to find this rate of change. So we're actually looking for dy dt here. When the base of the ladder is 7 feet from the wall, so when our x value equals 7. So we've read through our problem, we've identified everything that we know and everything that we're looking for. So now we can go ahead and take our relevant formula and we can differentiate with respect to t. So going through each, we have x squared plus y squared equals z squared. Taking the derivative of x squared, we get 2x, and then of course dx dt. Plus, taking the derivative of y squared, we get 2y dy dt. Equals taking the derivative of z squared, we get 2z dz dt. And we can leave it like that, or I'm actually going to factor a 2 out of both sides. So I have 2 times x dx dt plus y dy dt equals 2 times z dz dt, which means I can divide and cancel out those 2's. So I'm going to be using the formula, or using the differentiated formula, as x dx dt plus y dy dt equals z dz dt. And I'm just going to cloud that so I don't lose it. Okay, now that we've differentiated, it's time to substitute in everything that we know and then go ahead and solve. So plugging in, I know that x is 7, so I have 7 times dx dt, which they identified as 2, plus, now we have to plug in for y, but unfortunately, we didn't fill in a y in our known quantities. So in order to solve for y, we need to go ahead and use our original equation and the x and the z that we were given. This is like a bonus math problem hidden inside this problem. So using x as 7 and z as 25, we know that 7 squared plus y squared gives us 25 squared. So 7 squared is 49 plus y squared, and then 25 squared is 625. So we have y squared equals 625 minus 49 is just 576. Square rooting each side, we get our y value as 24. So just a little bit of fun bonus math hidden in there before we can actually plug in. So going back to what we were doing, plugging in a 24 for y, and then dy dt is what we are looking for. And that is equal to plugging in a 25 for z. And then dz dt is the rate of change of z of that ladder, and because our ladder is not changing, dz dt is equal to 0. From here, we can go ahead and just simplify as we know how. So 7 times 2 is 14 plus 24 dy dt equals 0. Subtracting 14, we are left with 24 dy dt equals negative 14. I forgot my units this whole entire time. So dy dt is equal to negative 14 over 24, which we could simplify to be negative 7 over 12, or rounding to the hundredths place, we would say negative 0.58, and now we need a unit. This is dy dt, so the rate at which the top of the ladder is moving down the wall would be feet per second. So for part B, it says consider the triangle formed by the side of the house, the ladder, and the ground. And this is referring to that very same ladder, so the 25-foot ladder that we were using earlier. It wants us to find the rate at which the area of the triangle is changing when the base of the ladder is that same 7 feet. So we're going to keep our x as 7. We already solved for y in our last slide and got 24. So here, because we're looking for the rate at which the area of the triangle is changing, what we're actually looking for is dA dt. Now, that means we can no longer use the Pythagorean theorem to relate these variables because we actually need to find a way to represent the area. Luckily, we have a right triangle, and we know the area of a triangle is equal to 1/2 the base times the height, where here our base is x and our height is y, so we have area equals 1/2 xy. And then I'm just going to list everything we know. So we know all three of our side lengths. We know x equals 7, y equals 24, and z equals 25. And then something additionally, so we know that the base of the ladder, from our last problem, dx dt, is changing at a rate of 2 feet per second. And we know that what we solved for in our last problem, dy dt, is equal to negative 0.58 feet per second. So we have a lot of information going into this. The first thing we want to do here is take our area equation, take our area formula, and differentiate with respect to t. Now this is going to be a lot of fun because we actually get to use the product rule. So here, taking the derivative of a with respect to t, we get dA dt equals, time for the product rule, we have our first as 1/2 x and our second as y. So here our product rule says the first times the derivative of the second. So here we have 1/2 x times the derivative of the second, which would be dy dt, plus the second, which is y, times the derivative of the first, and the derivative of 1/2 x would just be 1/2 dx dt. Now I'm actually going to just leave it like that, and we can go ahead and substitute in everything that we know. So we're looking to solve for dA dt. That's equal to leaving our 1/2, plugging in our 7 for x, and our negative 0.58 for dy dt. Remember, we got that from our last problem. Plus plugging in our 24 for y, we still have 1/2, and dx dt was given to us as 2. From here we can go ahead and solve. We have dA dt equals 1/2 times 7 times negative 0.58 is negative 2.03, plus 24 times 1/2 times 2, those are going to cancel out, and we're just left with 24. So we're left with dA dt equals, and we get 24 plus a negative 2.03 gives us 21.97. I forgot units again, but because we are changing area, we should be feet squared per second. Sorry about that. If you are confused on the units, just go ahead and ask your teacher to go back through. Okay, for our next problem, we have an airplane flying at an altitude of 5 miles passing directly over a radar antenna. When the plane is 10 miles past the antenna, the rate at which the distance between the antenna and the plane is changing is 240 miles per hour. What is the speed of the plane? Now this one is a lot harder for me to visualize without a picture, so I'm going to go ahead and draw a picture. So I want to draw my airplane flying at an altitude of 5 miles. So here's my 5 miles. My airplane is going this way. Looks like a bumblebee. And down here there is some kind of antenna. I have no idea how to draw an antenna. Like that. Okay, 5 miles past the directly antenna. When the plane is 10 miles past the antenna, so over here, the rate at which the distance between the antenna and the plane, so the distance is going to be this diagonal distance here, which means, look at that, we've created another right triangle. Now I'm going to go ahead and label my sides as I normally would, as my horizontal as x, my vertical as y, and my hypotenuse as z. Once again, relating my 3 sides. So here I want to look, what is the speed of the plane? Now when I say the speed of the plane, I mean how fast is it moving this way, which means what I'm really looking for is dx dt. So I want to relate my 3 sides, again using my good friend Pythagoras. So I can write this as x squared plus y squared equals z squared, and then let's go ahead and fill in everything that we know from this problem. So we know that x is 10 miles. I'm going to use units this time. Y is 5 miles. Oops. I'm so focused on my units I forgot to write the value. Okay, and we know, is that it? The distance between the antenna and the plane is changing at 240 miles per hour. So that would be the change in that diagonal, dz dt is 240 miles per hour. When we go to differentiate our function, or our formula, again, just like we did before, we would differentiate with respect to t, 2x dx dt plus 2y dy dt, equals 2z dz dt. Hopefully you recognize from the last problem that we can actually cancel all of those 2's out by factoring and dividing, so we can simplify this to be x dx dt plus y dy dt equals z dz dt. Now that we have differentiated and simplified, we can go ahead and start plugging things in. So we can plug in for x as 10 miles using units. Dx dt is what we are looking for. plus y is 5 miles. And then dy dt is going to be the rate of change of the altitude. And because the plane is going in a straight horizontal line, the altitude is actually not changing. So dy dt is going to be 0. And this is equal to z. Now we don't know what z is, but just like we could in the last problem, we can actually go ahead and use Pythagorean theorem to solve for z. So we have 10 squared plus 5 squared equals z squared, which gives us 100 plus 25 equals z squared. So z equals the square root of 125, which I'm actually just going to leave like that for now. So we have the square root of 125 times dz dt was given to us, hold up, square root of 125 miles. And then dz dt was given to us as 240 miles per hour. Okay, from here, I'm going to go ahead and start simplifying. So I'm going to leave this as 10 miles dx dt, that's what we're looking for, plus 5 miles times 0 is actually going to go away. And this is equal to 240 times the square root of 125. So square root of 125 is like 11.18 times 240 gives us 2,683.28, rounding to the nearest hundredth. And then I have miles times miles per hour gives me miles squared per hour. So then dividing by 10 miles on both sides, I get dx dt is equal to 268, rounding to the nearest hundredth, 0.33 miles per hour. Now just to clarify, when I did this, I rounded here in my work, but I left the full value in my calculator. And I didn't actually do any real rounding until the very end here, 268.33 miles per hour. Okay, here we go with another fun one. This says 2 cars start moving from the same point. Car A is traveling east at 100 kilometers per hour and car B is traveling south at 80 kilometers per hour. At what rate is the distance between them increasing 4 hours later? Again, another one that just reading it quickly, kind of a lot to think about, but if we draw a picture, it'll be much easier to visualize. So I'm going to start. It says 2 cars start from the same point, so let's pick a point. How about here? Car A is traveling east at 100 kilometers per hour. So over here is car A, and I think it's car A. And car B is traveling south at 80 kilometers per hour. They look like bugs. Okay, and then it says at what rate is the distance between them? Remember, the distance between them is going to be that diagonal, which means once again, we've created that right triangle that we are getting so used to drawing. I'm going to label my sides like I always would as X, Y, and Z just for consistency. And because I want to relate the sides of my triangle, I'm going to use my Pythagorean theorem. X squared plus Y squared equals Z squared. And I want to fill out my known and my unknown quantities, but I have to be really careful. Make sure that I'm reading it correctly. So this says car A is traveling east at 100 kilometers per hour. Kilometers per hour is how it's changing, so that's actually my derivative. So that's telling me my dx dt is 100 using my units, kilometer per hour. And then car B is traveling south at 80 kilometers per hour. So that's going to be my dy dt. And then we are looking for the rate that the distance between them is changing. So we want to find dz dt. Now, just like we have been in the last couple of problems, when we go to differentiate here with respect to t, we're going to get 2x dx dt plus 2y dy dt equals 2z dz dt. And that same trick that applied in those first two is also going to apply here. So we can write this as x dx dt plus y dy dt equals z dz dt. Now, looking at what I have, I'm going to need to plug in for x, y, and z, and unfortunately, I don't have any of those in my known quantities. So now I have to actually use the kilometers per hour, the speed that I was given, to find where those cars would be or what those values would be 4 hours later. So if car A is traveling at 100 kilometers per hour, 4 hours later, car A would have gotten 400 kilometers. So our x value is going to be 400 kilometers, just a basic 100 times 4. And then same idea, car B is moving at 80 kilometers per hour. 4 hours later, our car B would have gotten 320 kilometers. So our y value, I'm running out of room here, would be 320 kilometers. And hopefully you've guessed it by now. To find our third value, we can go ahead and actually use Pythagorean theorem. So we have x squared plus y squared equals z squared. So we have 400 squared plus 320 squared equals z squared. We're going to get some big numbers here. Let's do 400 squared plus 320 squared. And I'm going to square root this, square root. We get z is approximately 512.25, rounding to the hundredth there. So we've now solved for x, y, and z. We have dx dt, we have dy dt, and we are just looking to find dz dt. Now that we've found everything we need, we can go ahead and substitute in and then solve. Plugging in for x with 400 kilometers times dx dt is 100 kilometers per hour, plus plugging in for y at 320 kilometers times dy dt, which is 80 kilometers per hour. This is equal to z, which is 512.25 kilometers, and then dz dt, which is what we're looking for. A bit of multiplication required here. 400 times 100 gives us 40,000 kilometers squared per hour, plus 320 times 80 gives us 25,600 kilometers squared per hour is equal to 512.25 kilometers times dz dt. Okay, let's add. So we have 40,000 plus 25,600 gives us, running out of room, 65,600 kilometers squared per hour is equal to 512.25 kilometers dz dt. So we can go ahead and divide both sides by 512.25 kilometers. And we are left with dz dt, the rate that the distance between these two cars is increasing 4 hours later, would be equal to 65,600 divided by 512.25, 128.06 kilometers squared per hour divided by kilometers just gives us kilometers per hour. Okay, our last problem of the day A small balloon is released at a point 150 feet from an observer who is ground level. If the balloon goes straight up at a rate of 8 feet per second, how fast is the distance from the observer to the balloon increasing when the balloon is 50 feet high? Again, maybe you can see what's going on, but for me, I'm going to definitely sketch just a quick pic to make sure I know exactly where everything goes. So I have a small balloon. It's my balloon. Is released at a point 150 from an observer who is ground level. So here is my observer. Okay, and I am 150 feet from the observer and then obviously floating up because I am a balloon. And we're looking at the distance between the observer and the balloon, which is that diagonal, and once again, surprise, surprise, a right triangle. I'm going to go ahead and label my sides as I always would. My horizontal as X, my vertical as Y, and my diagonal as Z. Okay. From here, I want to relate my sides, x, y, and z, using Pythagorean theorem as x squared plus y squared equals z squared, and let's write what we know. A small balloon is released at a point 150 feet from the observer. So that means that this part here, this distance would be 150 feet. So I'm going to label my x as 150 feet. If the balloon goes straight up at a rate of 8 feet per second, so it's going up at a rate of 8 feet per second, that means that y is changing. Dy dt equals 8 feet per second. How fast is the distance from the observer to the balloon? Okay, meaning this dz dt is what we're looking for. How fast is that changing when the balloon is 50 feet high? So that means when y equals 50 feet. Okay, just like before, I want to go ahead and differentiate with respect to t. Pythagorean theorem becomes 2x dx dt plus 2y dy dt equals 2z dz dt. I'm sure you've already made the jump, but if you haven't, we can go ahead and get rid of those 2's now. Factoring and canceling, we get x dx dt plus y dy dt equals z dz dt. Plugging in what we know that x is 150 feet. Now dx dt is going to be the change in x, the rate at which that horizontal is changing. Because our balloon is floating straight up, dx dt is not changing, so it's actually equal to 0. Plus y, they told us, is 50 feet. Our balloon is 50 feet in the air, times dy dt is 8 feet per second, is equal to, now we need a value for z, and just like we did in the past couple of problems, we need to solve for z using Pythagorean theorem. So we have 150 squared plus 50 squared equals z squared. So I have 150 squared plus 50 squared, and take the square root, and we should get z is 158.11 feet. Plugging that in, I get 158.11 feet. And then dz dt is what we are looking for, so we can go ahead and leave that as dz dt. From here, our first term multiplied by 0 goes away, so we are left with 50 times 8 gives us 400 feet squared per second equals 158.11 feet times dz dt Dividing 158 by 11. We get dz dt, the rate at which the distance from the observer to the balloon is increasing, as 2.53 feet per second. Great job with these. I hope you enjoyed all of the exciting problems we can do with Pythagorean theorem and triangles with related rates. At this point, you can go ahead and complete homework number 24 in your 2.6 related rates homework packet. And if you have any additional questions about this section, you can go ahead and reach out to your teacher.